I didn't start it either yet because I knew you wouldn't help.
All right, so it's not that hard of a concept. All you have to do is set up your KSP for each sol. Ag plus times Cl minus equals KSP. Solve for Cl minus, that's the answer. KSP equals Pb plus 2 times Cl minus squared. Solve for x, that's the answer. So what do we get for this one?
1.8 times 10 to the negative 8.
1.8 times 10 to the negative 8 moles per liter of Cl minus. That's how much you need to precipitate this one. What do we get for this? 0.029. 0.029. That's how many, that's the moles per liter of Cl minus. Okay? So obviously you need way less Cl minus to precipitate this. That's a much smaller number than 0.029. So that makes sense. So you could actually figure this out. You could take whatever salt, figure out the molar mass, mass out how much you need to actually get that concentration, dump it in this container. All of this should theoretically start to precipitate, all right? And then you would have Pb plus 2 left over. But it's kind of tricky because that's when it first starts precipitation. So it's a little tricky. But anyways, you don't actually have to do that. So that's how you would do those problems. I'm only doing one of those. Those three, 61, 63, 111, similar to that. Okay, moving on. Last thing with KSP before we start talking about pH. Common ion, which we've already done a little bit. So common ion problems here. So common ion. So we did fractional precipitation very quickly there, but the concept I don't think is too hard. And the problems are kind of the same over and over again. They just change the salts. So common ion is very similar. Let's say we have, let's see, what do I have here? All right, well that's the sample problem. But let's say we have a saturated solution of silver chloride. So AgCl solid, Ag plus, and Cl minus. So let's say we have a saturated solution of that, and then we add some AgNO3. You could add solid or a solution, but if we add AgNO3 solid, let's say, to this equilibrium, what happens? What's the common ion? Right, so you're adding more Ag+, so the common ion is Ag+. So if you're adding more Ag+ to this solution, what would you expect to see? Shifting left, which what you would see precipitate. You would see particles start to fall to the bottom, so PPT will form because we shift left. So you're increasing the product concentration. So this is called common ion. This is nothing really new actually to you. You understand the concept of Le Chatelier's principle. You did it in lab. That was the point of doing the lab, is you see this happening. Okay, so I'm not going to spend a lot of time here. That's just one example. All right. So the way these problems work, they'll give you initial concentrations depending on which one they give you. Then they give you a concentration of something you add, and you have to figure out. Will it precipitate? Will it not precipitate? I have a problem right here. So anyways, that's the concept. Very, very simple, I think. Okay. So here's the question. All right. Calculate the solubility. Remember, that's grams per liter. Calculate the solubility of calcium fluoride. Calculate the solubility of CaF2, and that's in grams per liter. At 25 degrees Celsius, at 25 degrees Celsius in, and then you got a couple options here. A is pure water. We've already done that actually, so that's a little bit of review. B, so it's not a common ion problem yet, and then B would be in a 0.01 molar calcium nitrate solution. And then C, a 0.01 molar calcium fluoride solution. This was just like part, where are we here? Part B on the warm-up problem we did there. Part B 2 and 3. But part A, all you're solving for is the X in the KSP ice table. S, X, whatever. We did that before. So if you flip back in your notes, you can find a problem like that. I might have even done that, I don't remember. But and then these two, here's the concept. These ions are already in solution. I give you the concentration, so that's the concentration you know. You just have to figure out the concentration that you don't know in the KSP equation. So I give you, obviously the common ion is Ca and then F. So I give you that, you have to calculate the other one. Trying to decide if I need to give you a little more help here. Everyone should be able to do part A, is what I'm saying with that. All right, I'll give you one more piece of advice. So for part B and C, you're going to set up the ice table with calcium fluoride. That's your initial of Ca. That's your initial of F. Set up your ICE, and then you're going to use the E equal to KSP. Oh, I got to give that to you, don't I? Yeah, sorry. That would help. KSP of CAF, so this KSP is 3.9 times 10 to the negative 11. That would help. So again, let me repeat that. For part B and C, 0.01 is your initial concentration of Ca and F. Do your ice table, use the equilibrium concentrations, plug them in the KSP equation, solve for X. I'm going to say one more thing and let you go. Is this number really small?
Yes.
Yep. So you're going to have a weird number in your ice table. You can ignore one of the X's because that's so small. Remember I told you that last week? Or whenever that was. We'll just see how you get. We'll see how you get. Go ahead. I gotta run to the little boys' room real quick.